rooms yesterday. So there may be a few people joining as we begin. But let me start. I'd like to welcome everybody to our ESIDHA breakout on robotics and autonomous systems. My name is Claire Tomlin. I'm with EECS at Berkeley, and I'm co-organizing this with Magnus Egerstedt, who is one of the organizers of this whole meeting, robotics aficionado and Dean of Engineering at UC Irvine now. So over the next 2 hours, a little bit less than 2 hours now, we have 4 exciting talks speaking to the future in robotics and autonomous systems. Then we'll have a link to some corporate suites, after which we'll return for a panel discussion with our speakers. And I think it's a kind of nice introduction after that great morning of awards and keynotes to think back to a few things that were said in the keynotes, in particular in Dr. Margaret Martinosi from NSF SIZE, her talk. And as she brought up the tire tracks diagram that I think those of you who were there saw, in particular the track on automation and robotics, what was really kind of clear to me from that diagram was how much has happened in the transfer from university and industry R&D to products and services in the recent decades. So she had this timeline from the 1960s. And you saw, in other areas like, networking, communications, computer architecture, there was kind of this constant transfer from the R&D to the products and services track. Whereas in robotics and automation, there's a big emphasis in the past few decades. And, we've all been seeing that. I think it's one of the most exciting things. And I know our speakers are going to speak to this in their talks. So I'd like to, without further ado, get started. We have, as I said, 4 speakers, Professor Daniela Roos, Professor Ken Goldberg, Professor Angela Schulig, and Mark Easley, who are going to talk. And I'm going to start by introducing our first speaker, Professor Daniela Roos. Let me give a brief introduction to Daniela. She is the Andrew and Erna Viterbi Professor of EECS at MIT. She's also the director of the CS and AI Lab, the famous CSAIL lab at MIT. And she directs the Toyota CSAIL Joint Research Center there. She's also the Deputy Dean for Research in the Schwarzman College of Computing at MIT. Daniela works in robotics and AI and data science, and she works in the tools and technologies to increase the ability for robotics and autonomous vehicles to reason and learn and adapt to complex tasks in human-centered environments. And as such, she brings in and works with tools in human cognition, for example. She works in the domains of transportation, manufacturing, agriculture, construction, as well as many others, and has won numerous awards. She's a MacArthur Fellow. She's a member of the National Academy of Engineering and the American Academy of Arts and Sciences. And she won the 2017 Engelberger Robotics Award from the Robotics Industries Association. Daniela.
Thank you so much, Claire, for that very warm introduction. Let me make sure that technology works. So let's see. Does the screen share correctly?
Yes, it does.
Okay, super. So that was a very exciting talk, very inspiring. As I think about the future of technology, I see tremendous opportunities. Because today, telepresence enables us to participate in the session together. And technology enables students to meet with teachers and doctors to treat patients that are thousands of miles away. Robots already help with packing on factory floors, and network sensors enable monitoring of facilities. 3D printing creates customized goods. We are surrounded by a world of possibilities, and these possibilities will only get larger as we start to imagine what we can do with advances and progress in artificial intelligence, machine learning, and robotics. So imagine waking up enabled by your personal assistant that figures out the optimal time and helps you organize everything you need for the day. And here comes the personal assistant. Okay, so then as you walk by a store, the image in the store window displays a picture with the latest fashion on your on an image of yourself. And inside the store, if you choose to buy a shoe, a robot could analyze the walking style, take a 3D photo of the foot, and make a bespoke shoe on the spot. And when you meet friends, you can even change the color of your tops to match each other. Now at work, inside the intelligent boardroom, the temperature would be adjusted automatically by monitoring people's comfort levels, and gestures can be used to pull up holographic diagrams of the things that are being discussed. For example, a new design for a flying car. Um, and back at home, when you take your first ride on a bike, adaptable wheels could appear and disappear according to your skill level. A robot helps with planting a garden, and a different robot can deliver the items you purchased earlier in the day, and garbage bins take themselves out. And after a day, when it's time for a bedtime story, you might be able to enter the story and interact with a dragon. In a world so changed by computing that has enabled so much for us, what might it take to get to the kind of future that I imagine? What kind of work will we be able to offload to machines to increase the quality of our lives and save lives? Imagine driving home in your autonomous car, knowing that your vehicle can get you there safely and even make your commute relaxing. You stop at the store to pick up groceries, and when you walk in the door, you hand over the dinner menu to a robot that connects with your house and immediately brings a box with all the things that you need. These are the kinds of possibilities about the future enhanced by robots helping us with cognitive and physical work. And you might say, or you might be thinking that this sounds like one of those cartoons about the future that never quite comes to pass. But that future is not that far off, because today robots have already become partners in industrial and domestic settings. And in the future, AI assistants, whether embodied or not, will be our guardian angels and our smart tools that are supporting us with physical and cognitive tasks. Now, I have been working for decades to help build a world in which machines are helpful, not a world in which machines take over nor solve all of our problems. And this kind of vision about the future is really starting to mature in the labs of my good friends and in my lab, at labs at other universities and across the world. It's a vision that I have been fascinated with for a long time. Since I was a kid, when I loved the science fiction books of Jules Verne and the movies of Jacques Cousteau, I often immersed myself in reading and imagined journeying to faraway places. And years later, after I learned how to make and code robots, and when I met a student who also loved the books of Jules Verne and the movies of Jacques Cousteau, we decided to build a robot together. It was our own version of the 20,000 Leagues Under the Sea Observatory. We call this robot Amour, which stood for Autonomous Optical Underwater Robot. But building this robot was really about love. Amour was lovable, agile, and nimble. It moved elegantly like an underwater helicopter. It took beautiful photos, and it could transmit them in high resolution video. All of these capabilities were enabled by innovative ideas. Now, one very hot summer day, we were off the coast of Singapore after some experiments with sponsors, and we decided to see just how fast Amour could go. We were feeling confident that day, and we took off several safety components of Amour to give it more juice, and then off the robot went. Well, I should tell you that it took us 3 years to develop this robot, and this was our only unit. And then we waited and waited and waited, but Amour did not return, and we were devastated. Now, the thing about the work we do in robotics is that the first instance of a robot takes enormous amount of time to develop, but subsequent versions take much less time. And it is also the case that great failures teach us great lessons. So we went back to the lab, and within 90 days, we made 3 improved versions of this robot. And with great hope, we took the new robots to water, and indeed they could swim, but we found ourselves wanting more. We wanted smaller, nimbler, more elegant robots. And that's how we got to build the robot fish, which you see in this picture. It's a robot that has a soft tail enabled by by novel engineering approaches to new materials. And this tail can flip back and forth for swimming. The fish is very agile. It can change the swimming direction in about 100 milliseconds, which is the same time as for a real fish. And this is called the escape maneuver because it allows little fish to escape from the big fish who want to eat them. And then we took the soft robot fish to the ocean where we had a chance to swim with it, and that's me next to the robot. And we watched this robot glide by beautiful corals. Sorry about that. Our fish encountered many schools of fish with its cameras, and it even found Nemo. So it took us 3 years to make Amour, 2 months to make 3 copies of Amour, and today we can make the soft robot fish in the lab in a few days. And this rapid change of pace is extraordinary and may sound familiar to all of you, as we think about how 2 decades ago computation was a task reserved for the few, because computers were large and expensive and hard to access, and the person needed a level of expertise in order to know what to do with them. But all that changed with the smartphone. And today, computation has become so normal, we have stopped noticing how central it has become to almost every part of our lives. And this raises an important question. In this world so changed by computation, what could it be if we have robots, machine learning, AI, helping us with physical and cognitive tasks? Well, such a world requires that we address 2 challenges. Specifically, robots are made of a body and a brain. And for every task, we need a body that is capable of doing that task. And we need a brain that is able to control the body to do the task. Right now, robots are made from scratch, and it requires real expertise. And similarly with control. So a natural question is, how can we use new tools to automate those aspects of making machines? Well, one solution is inspired by nature. All organisms in nature are made of cells that combine in different ways to make organisms such as snakes and ants, and organs such as lungs and hearts. So the question is, can we have robotic cells that can be composed in different ways to make different types of robot organisms? And here's a simulation that shows how a couch robot could become a dog robot. In this case, the cell is a cube that expands and contracts by a factor of 2. And the simulation shows that the computation solution for doing this is already here. But we still need to make the cell, and we do not know how to make it at a scale where the couch will be comfortable to sit on. Now, the kinds of unit cells we can make today are too big to make comfortable dog couches, but we can make simpler things like shape-shifting trusses and support beams. And here you can see one example, the M-block. This robot is a 2 by 2 inch cube that can move by pivoting. And the secret to the movement is a flywheel inside the robot that spins very fast, and then a braking mechanism stops it suddenly. The stored momentum propels the cube forward. And we call it the M-block because the M stands for magic. The robot moves as though by magic. Now, to get from something like M-block, which we already have, to a dog coach, which we aspire to have, we need to make these robotic cells softer, smaller, more like materials. We need to bring materials and machines closer together. And for that, we need students that are trained both on the hardware aspects and the material aspects and the computational aspects of machines. And we are all striving to do that. But we can also do more. So what, we can build these modules at a larger scale. And while we can't have comfortable modular couches, what we can have is applications where self-configuring modular robots are built at larger scales. For example, floating robotic boats that can carry people and goods, and that can self-assemble to make autonomous floating platforms for people to gather for events, for markets, that can aggregate just on time a water bus stop. For instance, here you can see these robotic boats, and you can see the concept of how they will form the water-based stop. And then you can augment these robotic arms for autonomous trash collection. Now we are on our way to create such self-organizing robots we call robots. And here you can see a simple example of creating an autonomous platform made of multiple independent units at quarter scale. And this is the quarter scale of what we are planning for a full scale. And by the way, the full scale is currently under development in Amsterdam. And you can see what the half scale looks like here. The full scale is being tested in Amsterdam as we speak. Now, what's really cool about these robotic boats is that the same autonomy algorithms and systems that make robotic cars able to drive on roads also allow these robotic boats to drive to move on water. Okay, while we continue our work on robot cells, we have a parallel second option, and that is to develop the coding tools that automate the design of custom robots and the making tools that automate their fabrication. And this takes us closer to a world where you can imagine people having one robot for any physical task. And here's how this might look in the future. Take Alice. We'd like to give her the power to automate many tasks in her home. Say she wants a playmate for her cat for when she's at work. Well, to do so, Alice would go to a new store called 24-Hour Robot Manufacturing with a rough idea of what playmate she wants. At the store, she would explore the design space for her device with an intuitive interface, and the store will fabricate the robot at an affordable price point, and will also create the programming and control infrastructure for the robot. Well, this is not possible today, but we are slowly developing the tools that will get us closer to this vision. In particular, my research group at CCEL is working on this problem. And so let's say Alice wants to play chess with a robot. The solution is to have a program decode the instruction, determine behavior such as pick up piece, move piece, drop off piece, and then send off the design to be fabricated and assembled. And we call the robots we do this way origami robots because they're created by folding. And we were inspired by the ancient art of origami. And here is the robot car. And I have to say, I forgot to turn my my timer, so I'm not sure how much time there is left.
Daniela, you have about 3 minutes left.
Okay. So we can automate the design of these robots. For instance, this robot starts as a flat piece of plastic. When you put it on a heating pad, it self-folds into a fully fledged robot that can run and carry a load. And the way we automate this design process is conceptualized in this slide. The idea is you can take any 3D object, for example, this bunny, and you can make it by folding layers with the correct geometry. By using some new algorithms and off-the-shelf software, we can unfold the design, 3D print it, and then turn it into actual robotic devices that can be controlled. So using this approach, we can automate the design and fabrication of a wide range of objects. We have an alternative solution we are working on, and that is grammar-based, that brings computation and engineering together. And the idea here is to identify all the kind of mechanical components, electromechanical components for the robot, and create grammar rules for how to blend them. And then we can use machine learning coupled with optimization to transform to search the entire design space. And I should click to search the entire design space and develop designs that are optimized or co-optimized, where the body and the control system of the design is co-optimized for a task. So for instance, this is what the system found for running fast over a terrain with gaps. You can change the specification to flat terrain or stairs or any other type of terrain, and you can get new types of machines in this way. And then we can, given that the grammar is rooted into mechanical components, we can then take these designs and quite quickly adapt them to fabricable designs. So using this approach, we can bring materials and machines closer together. We can invent new types of robots that are optimized for tasks. We can code those robots. We can really get closer to a vision where we can easily and rapidly synthesize one robot for any task. This naturally brings the world of computing with the world of hardware together. The way I see it, those of us who know how to make things and breathe life into them through programming, those of us have superpowers, because we can make real anything that we imagine. And so I think this is a great aspiration for all of the students who are coming to our EE and CS and computer engineering departments. I would really love to see all of our students leave our departments with this kind of superpower. Thank you very much.
Thank you, Daniela. Thanks for that exciting and kind of visionary talk. Now, we are going to have a panel discussion after, in the latter part of the session, but unfortunately, Daniela won't be available for that. So I suggest that we take just a couple minutes now to ask Daniela any questions that we may have of her at this point, since she won't be joining the panel later. And maybe I'll, or Magnus, you always have a question, so why don't you start?
Yeah, I always have questions. So first of all, I'm sorry I'm late. I actually lost Wi-Fi connectivity for a sec there. But apparently Claire called me a robotics aficionado, so I was very happy to hear that, even though I missed it. But Daniela, this was amazing. How do we get the superpowers? So as department chairs and school chairs here, who are actually in the middle of imagining what our new curricula should look like, I really like the idea of empowering or endowing our students with superpowers. How would you, if you were in charge of the EC program at Georgia Tech, how would you structure it?
Well, I think that it's important for students to learn how to make things. And so in other words, the hardware part is super important. Because that's what makes the body of the machine. And whether you make a robot or an NVIDIA board, and understanding the body and understanding how to customize and optimize the body to deliver on the task that it has to do is super important. And then on top of that, we need to understand what kind of control systems are available, or how to think about control. And so to me, superpower becomes real when you are able to imagine something, when you can realize the body, and then you can actually control what the body does. So that means we need to teach our students about hardware. We need to teach our students about computation. We need to teach our students about the bridge between hardware and computation, but also we need to teach our students about the new tools, the machine learning, the AI, the optimization tools that are being introduced in our world at an extraordinarily rapid pace. At MIT, we have one of the only combined EECS departments that remains combined in our country. And so we recently went through reorganization step where we took our large EECS department and we organized it in three faculty and these faculty are all part of the same department. We have EE, we have CS, and we have AI plus D. And we told our faculty to self-select in each of these groupings. The interesting thing is that we had about the same number of faculty self-select for each group, and a large fraction of our faculty wanted to be in multiple groups. And so that I think that speaks to the fact that the future the future involves a combination of hardware. It involves a combination of hardware with computation and with higher level reasoning tools that we can place on top of that. And so it's a tall order to teach our students about all these things, but we can imagine rehashing or reworking the curriculum so that it is possible to touch in substantive ways on all these three areas.
And Daniela, how do you incorporate, or maybe on behalf of MIT, how do you incorporate the social aspect? So you're designing robotic systems that are working in populations, working closely with people. How do you ensure that the social, not just sort of the cognitive, but the kind of, societal aspects, and that the students are knowledgeable and educated in aspects of how to, and diversity and how to interact in society?
That's a really great question, Claire. The EECS department and CSAIL are both part of the Schwarzman College of Computing. And when the college was founded, there were three principles for the college. One is to advance the computing disciplines. The other was to advance computing across fields. And the third was responsible uses of computing. And so, in some sense, this notion that we have to be responsible for the work that we do, that we have to train the students in ethics, that we have to train the students how to think responsibly, is the foundational part of our new larger organization structure at MIT. And within this, or with this objective in mind, one thing MIT has done over the past year is to collect together case studies that look at responsible aspects of computing and at ethical aspects of using computing. And these case studies were written by faculty from across the world, not just by MIT faculty. So we're building an ever-growing collection of these types of case studies. We're using the case studies in every course we teach. So the philosophy is to not separate the teaching of responsible computing from the teaching of the domain or the technical aspects of the course, but rather to have some kind of blending of the two, and to do so through these case studies that allow us to have discussions and debates and really bring awareness.
So Daniela, I'm gonna actually have to jump in, because I was told that they're gonna pull the plug at one point and just put us into the corporate suites, and I want to make sure we progress. But you have tons of questions in the chat, and before you leave, would you mind taking a look at those and sharing some of your thoughts, particularly how one transitions from a university that's not MIT to a smaller, maybe perhaps less well-endowed university. So I'm sorry I jumped in, but
of course, I'm sorry I'm speaking too much. So
no,
great presentation.
Yeah.
Thank you so much, Daniela, and thank you very much this morning. Okay, I'd like to now move on to introduce our second speaker, Professor Ken Goldberg. Ken is the William S. Floyd Professor of Industrial Engineering and Operations Research and EECS at Berkeley. He also has appointments in the School of Information, the School of Art Practice, and the UCSF Department of Radiation Oncology. Ken is one of the founders, and he leads the Berkeley AI Research Center, which brings together a large number of researchers across the university in AI and associated areas. And he's also heads his startup, which is called AMBI, for ambidextrous robotics, which is super fast pick and placing tasks by robotic arms in industrial settings. Ken is a specialist in robotics, automation, and social information filtering. His research focuses on the interplay between machine learning and model-based techniques in robotics and automation. And he focuses on designing robotics that have very high performance, but are also safe, and understanding their safety. Ken is also an artist. His art installations have been shown at the Whitney Biennial, the Berkeley Art Museum, the San Francisco Contemporary Jewish Museum, and other places, including the Pompidou Center. He has 3 Sundance documentary films, and he's won a number of awards, including a Presidential Faculty Fellowship, the NSF Faculty Fellowship, and the Joseph Engelberger Robotics Award in 2000. Welcome, Ken.
Thank you, Claire. I really appreciate that. I am really delighted to be here. I appreciate that you and Magnus invited me, and I want to say at the outset that I can relate. My undergrad degree was a double E from UPenn, and I saw that George Pappas is here, so shout out to my alma mater. I want to talk to you really quickly about some trends I see in regard to robotics and automation. And I also want to acknowledge we're right now in the phase of celebrating the wonderful graduates who are now incredibly resilient because they just went through something that no undergraduates have gone through before. I want to put the idea of robotics into context. We recently celebrated the 100-year anniversary of the word robot. It was coined in a theatrical play in 1920. In contrast, that word automation was coined in 1948 at Ford Motor Company, and this was a term to describe robots that worked on assembly lines. Now, I want to just make a distinction here because I think it's subtle, but it's very relevant to the discussion today, which is about academics and curriculum around ECE. And so there's a subtle distinction between robotics and automation. And I've been working with a group who we came up with this diagram, this Venn diagram, where we say that robotics has its own conferences, et cetera, and is focused on oftentimes proof of concept, doing something for the first time. In contrast, automation has other conferences, but its focus is on taking a concept and now making it work reliably, efficiently, cost effectively over a period of time. That's where you take something out of the robot, out of the lab, and put it into practice. Now, the sweet spot I see is that there's these rapidly growing areas we've talked about earlier where these all come together when the robotics and automation come together with applications. And this is growing tremendously, as Daniela alluded earlier. And I think there's enormous synergies between the automation and the robotics sides of this. Now, there's a huge number of startups, and this is I think we can all relate that our undergraduates have a growing appetite for getting involved with startups. So I think this could be, is very important to essentially accommodate that by helping them learn some of the skills that are required for startup companies. Some of the areas that I'm very excited about, one is home automation, and it's because of this changing population. So this diagram illustrates this very, I think, effectively, where in 1990, there were about 6 working people for every retired person. In 2000, we were down to 4. And we're very close to being at the point where there's only 2 working people for every retired person. This is the demographic world we're living in. And I am a baby boomer, as my teenage daughters remind me. And so the boomer generation is going to be a massive, essentially, burden on the rest of society. So unless we could develop technologies to address it. Now, by that I mean being able to take care of seniors and allow them to age in place. So one thing that would be very helpful, for example, would be something like this. This is a very common scene, at least at my house. And it'd be nice to be able to go away for a few hours and come back and have everything nicely straightened up. It's very good for morale, but it's also good for safety because you don't want things to be laying around that people could trip over. Now, I also want to address the big elephant in the room. We've been everything has changed. It was very akin to being hit by an asteroid, and we are coming out of it now, and I'm very excited about that. But it's changed our attitudes toward robotics and automation. So we're now embracing robots in new ways because they're safe. They can move about in areas where there may be viruses. They were also used for disinfecting, and they've been used in this application, which I don't think existed before COVID-19, but disinfecting stadiums. And Angela will talk more about the huge, vast growing area of drones and flying robots. They're also being used in healthcare to allow people to communicate with loved ones who are potentially contagious. And the whole field of telehealth has changed remarkably in the last year. People have just learned to accept it, and I think this is going to persist after the pandemic ends. There's other applications like home delivery, which spiked during the pandemic, and this is the one I want to touch on for a few minutes, which is e-commerce, deliveries to our homes. And this is not uncommon. I think all of us can relate to that. This is actually a photo of my front porch on a typical day, and we're all just getting a huge amount of deliveries. Now, e-commerce has been growing over the past decade, but this year it spiked. It was a huge increase in e-commerce for obvious reasons. People are at home and they didn't want to go out, and e-commerce just filled the gap. Now, here's the challenge is that at these delivery centers, the warehouses, there is a huge glut of packages. The demand is so large, and it's hard to find workers to fulfill that demand. So, and why is this an issue? Because there's a huge amount of the process of handling packages has to be done by hand. It can't yet be automated, or hasn't yet. Now, a grand challenge that has been recognized is that if we could figure this out, if we could figure out how to allow robots to pick up an arbitrary object, that would be, if we could solve that grand challenge, it would enable innovations in homes, warehouses, and factories. And my PhD student, Jeff Mahler, did his PhD where we studied this problem from a variety of perspectives. And DexNet, or DexterityNet, was inspired by ImageNet. And ImageNet, as you all know in deep learning, was a breakthrough by having millions of labeled images. So our idea is to do something very analogous, to have millions of labeled three-dimensional grasps. And that's DexNet. So that, and I won't go into the details here, but we analyze each particular grasp, and for a typical object with 1,000 facets, for a parallel jaw gripper, there's 1 million possible grasps. So for each grasp, we want to analyze it for robustness. In other words, how robust is it to small perturbations in the relative pose of the gripper and the object, and also to parameters such as the center of mass and friction. And then we use Monte Carlo integration to add this up to come up with an estimate of the reliability of different grasps. And as you can see on the left, this grasp is not as reliable as the one on the right because it has a sort of self-correcting. It's more tolerant to these small perturbations. That analysis can be done overnight for millions of objects, and that provides a data set. We then use that to train a deep neural network. A set of parameters, this theta star that minimizes the loss between what our data and the output of the network. And the result is a system that was surprisingly effective at grasping novel objects. So none of these objects you see here were ever part of the training set. And it had essentially learned how to find grasp points. So I've been working on this problem for 35 years, and I like to say I've made very little progress, but this was something new. This is very exciting. So we published a number of the papers on this, and then as Claire mentioned, we started a company. And I'm going to just show you, I won't go into the detail here, but I just want to show you a video of the system that we just recently announced. This is for packages is operating in a real warehouse facility. Now, that system was a result of 4 amazing students, a mix of computer scientists, electrical engineers, and mechanical engineers. And they were the co-founders of the company, and it's such a pleasure to watch this system actually doing work in the real world. And this field of logistics, I think, is a sweet spot for robotics because it's somewhat fault tolerant. You can drop a package every once in a while, and it's not the end of the world, unlike self-driving cars. I also want to mention that I see the huge opportunities in surgical robotics, and we can talk more about that later, and in agriculture. I want to tell you very quickly a story about something very relevant to what Daniela just mentioned about design. And for this we have to go to the continent of Africa. I was actually born there in Nigeria in 1961. And I went back with my mother recently, and we toured a number of universities and met students who actually shared a great love of robots. We found that they were using robotic kits, such as this Lego Mindstorms, but it was, with the cost of $300, was prohibitive for students. They would often have the robot system in their village for, let's say, 2 weeks, and then it would have to be moved on because they were sharing it from over dozens of schools. So with some of the faculty there, Aorcor Corsa in particular, we formed the African Robotics Network, AFRON, to bring together researchers and students and anyone interested in robotics in the continent of Africa. And we put out a challenge, which was to design an ultra affordable robot. And we set an impossible goal there of $10. We wanted to see if anybody could design a robot for education, programmable robot, that would cost less than $10. So we had a prize competition. We got submissions from all over the world, very interesting devices and very clever, but none of them were close to the target of $10, except one. An inventor in Thailand who was a hobbyist would in his spare time, he would take apart game controllers like the Sony game controller. What he did was he modified one of them to turn it into a robot. He took the vibrating motors and turned them around so they could drive wheels. And then he wanted to have the thumb switches activate when the robot came into contact, bumped into a wall, say, and that would switch it to reverse. So he was looking around for some kind of counterweights, and he came up with a stroke of genius that he decided to put 2 lollipops on the system as counterweights. So this was born, the Lollibot, which was a fantastic design, and all the information is on this. By the way, if you search on the web, you will find a specification how to build your own, down to every resistor, etc. And what's amazing part about this is that the total cost for this robot is $8.64. So this is the power of ingenuity, and it comes from many different sources. This is a thing I really want to emphasize, is that we are training a new generation of diverse engineers, and the key is to bring together people with very different backgrounds. I think there's been a trend in education, not only in engineering, but in many aspects of STEM education, which is about conformity. Being consistent, being obedient, getting everything just right. That's very important, I agree. But we also need to be emphasizing this other aspect of creativity. And that means diversity, being able to interact with people who are very different than oneself, and being tolerant of variety and change, and knowing how to collaborate and innovate together. So I put together this slide of what Magnus had mentioned, like, what would you recommend teaching ECE students? So I have a lot more to say about this in the panel, but I just put this together. It's an ABCs. So the first is always be coachable. And by that, I mean, this is something that I try to teach my daughters, and I even try to teach myself, which is to always take in input, be receptive to input, seek it out. Then diversify, enjoy freedom of inquiry, and fail gracefully. Give back, and this is my student again, Jeff Mahler, who's teaching and showing students who came to visit our lab. Have fun and take initiative. Join ideas. That, in other words, if you take 2 different ideas and put them together, you often come up with something really new and exciting. Know your audience. So if you're giving a talk to department heads of ECE, then you change your talk so that it matches their interests and their expectations. Leadership goes without saying. Mentor and be mentored. Negotiate, but don't over negotiate. That was that comes in especially relevant when you're accepting a new faculty job. Publish, question, risk, share code and data, and credit. That's something I really believe in, which is don't be stingy about credit. There's no benefit to that. Many of our papers have 8, 10, 12 authors on them, but that's, I feel, very important to give students exposure. Take breaks, celebrate your achievements, understand things, volunteer, work hard, examine your biases, say yes. When you're asked if you want to volunteer for something, say yes, and be zealous. Just embrace the world around you. All right, I'm going to skip this and just say I'm very excited about the potential at post-pandemic. Everyone knows that this was voted by Congress last week to earmark $250 billion from the Congress for technology and specifically around topics that are relevant to ECE and robotics and microchips. I want to thank, in particular, my students. I have I could do nothing without them, and the sponsors. The same thing is true. And if you want to follow up with me, this is my contact information. This is from a book we put together called How to Train Your Robot last year, and that is me in the middle of the that scene. All right, thank you for your time and attention.